Hello, AP Chemers. Last time we met, we talked about the law of definite composition, and we did do this first problem here. So today we're going to start with this one where it says if one heats 1.725 grams of carbon in a hydrogen atmosphere, the resulting compound has a mass of 2.300 grams. We want to calculate the empirical formula of the compound. So what they're telling us is we have some carbon, and we're going to put this in a hydrogen-rich atmosphere. And it seems like a reaction happens because you form a compound, and they tell us that this compound forms. So that compound must have some hydrogens and carbons, the hydrocarbon. Now, we don't know what X and Y are, and that's what they're asking for. When they're asking for whether it's an empirical formula or a molecular formula, they basically want to know what those numbers are. So the X and the Y, those numbers, are the number of atoms or moles. I should say the ratio of atoms or moles. So the ratio of atoms of carbon to atoms of hydrogen, or the ratio of moles of carbon to moles of hydrogen. So what you want to do is find either the number of atoms or the number of moles of each and compare them to find the ratio. It's much easier to find moles than it is atoms, so that's what we're going to do. So we're going to start with the 1.725 grams of carbon, change that to moles. And then that gives us 0.1436 moles of carbon. And we're going to do the same thing for hydrogen, except they don't give us the grams of hydrogen. They do give us the mass of my products and the mass of the carbon. And we know, based on the law of conservation of mass, that the mass of my products should equal to the total mass of my reactants, right? So if I take the mass of my products, subtract the carbon, I would get the mass of the hydrogen. So 2.300 grams total minus 1.725 grams of carbon. That gives me 0.575 grams of the hydrogen, and then we're going to convert that to moles. So it's 0.575 moles of hydrogen. So great, we figured out that the X is 0.1436, the Y is 0.575. Problem is, those X and Y need to be whole numbers. They can't be decimals. So if you're good with math and you are able to look at these numbers and figure out what the ratio is right away, great. If you can't, which most of us can't, then what you can do is you can divide by the lowest number. So out of those two numbers, this is smaller, so I'm going to divide by that. This gives me 1. This gives me 3.94, which is about 4. If it's 0.9 something or 0.1 something, it's okay to round. If it's like 0.5, then you can't round. So my empirical formula is C, just 1, and then H4. CH4 is my answer. All right, let's take a look at the next one. It says if chromium 3 oxide is obtained from chromium ore, that's 99% pure, how many kilograms of chromium can be purified from 1.0 ton of ore? So most metals that are found on Earth, like in the Earth's crust and so on in nature basically, are found as ores. And ore means that this metal is in the form of an oxide, so it's bonded to oxygen. But typically, it also has some extra impurities in there. And so they're telling us that this chromium is found in an ore. And so there's chromium 3 oxide. 99% of this ore is chromium 3 oxide. And then 1% is impurities. So the question is, how many kilograms of chromium can I get from 1 ton of this ore? So first of all, it says chromium 3 oxide. Let's figure out what that is. So chromium 3 means it's Cr3 plus. Oxide is O2 minus, so chromium 3 oxide is Cr2O3. Next thing I want to do is I don't like this 1 ton. I don't like the English system, so I'm going to convert that first to metric system. So I know that a ton is 2,000 pounds. And I know that a pound is 454 grams. Now, any of these conversions right here, you would be told what they are. You do not need to memorize the conversions that are in the English system. But this gives me grams of ore, right? And it might be helpful to just find chromium oxide. So I know that I need to multiply this by 0.99 in order to get how much chromium oxide. Now, you can write it this way, or another way to write it would be for every 99 grams of Cr2O3, there's 100 grams of ore. You could do it that way as well, and that will give you grams of chromium 3 oxide. So when you do this, you get, say, it's a really big number. Yep, so you get 898,920 grams of chromium 3 oxide. So then what do we do with that? Well, we didn't want just chromium 3 oxide, we wanted chromium. So what I could do is start out with this number again. And then I can use my molar ratio to go to chromium. So in order to go to the molar ratio, I need to go to moles of the chromium oxide. 1 mole of Cr2O3. Molar mass is 152 grams. Then now we can do the molar ratio, moles of chromium oxide. 2 moles of chromium. There are 2 moles of chromium for every 1 mole of chromium oxide. And then I want kilograms, so I'm going to go to grams. 1 mole of chromium is 52.0 grams, and then to kilograms. 1,000 grams for every 1 kilogram. After all that, you get, with sig figs, you have 2 numbers here in 110, so 2 sig figs I should say. So 610 kilograms of chromium. Pretty cool, right? Okay, let's look at this next one. It says a compound is determined to be 1.2% hydrogen, 24.7% calcium, and 14.8% carbon, and then 59.3% oxygen. We want to know what is the empirical formula. So remember that if we're asked for the empirical formula, I have some hydrogen, I have some calcium, some carbon, and I have some oxygen. So W, X, Y, and Z. So basically I'm trying to find what those are. W, X, Y, and Z, what those numbers are. Remember, these are the ratio of atoms or the ratio of moles. So I want to find either the atoms or the moles of each of these and compare. Easier to find moles than it is atoms, so I'm going to go ahead and do that. Now, they don't tell us what the masses are, but they give us percentages. And remember that if my compound is 1.2% hydrogen, whether I have a gram of it or 100,000 grams of it, it's still going to be 1.2% hydrogen. So you can look at any size sample that you want. My recommendation, if you're given percentages, is to look at a 100-gram sample. So I'm going to say in a 100-gram sample, I would have 1.2 grams of hydrogen, 24.7 grams of calcium, 14.8 grams of carbon, and 59.3 grams of oxygen. And I'm going to go ahead and convert all of these to moles. So 1 mole of hydrogen is 1 gram. 1 mole of calcium is 40 grams. 1 mole of carbon is 12 grams. 1 mole of oxygen is 16 grams. Let's see, so this one's 1.2 moles of hydrogen. This one is 0.6163 moles of calcium. This one is 1.232 moles of carbon. .71 moles of oxygen. Again, if you can look at these numbers and be able to tell what the ratio is, that's great. If not, then divide by the lowest number. So I'm going to go ahead and divide by the lowest number, which is 0.61, it seems like. 616. So this gives you 1. This gives you 2, this gives you 2, and this gives you pretty close to 6. So my empirical formula then would be H2, calcium, just one of those, C2, and then O6, and that is my empirical formula. All right, let's take a look at the next one here. So it says nicotine. Nicotine is like the addictive ingredient in cigarettes. So nicotine is 74% carbon, 8.7% hydrogen, and 17.3% nitrogen. It says the molecular mass of nicotine is 162 grams. What is the molecular formula of nicotine? So again, I have a compound that is made of, let me go ahead and change the color here. I have carbon, I have hydrogen, and I have nitrogen, and these are my X, Y, and Z that I'm trying to find. The X, Y, and Z are the ratio of atoms or the ratio of moles. So we either find atoms or moles. So I'm going to find moles. I'm not given masses, and I'm given percentages again. So I actually have 2 different ways of doing this problem here. The first way is to do it the same way as we did this one, this above problem. So we're given percentages, so we said, well, we're going to look at a 100-gram sample, And then in the 100-gram sample, we'd have, in this case, 74 grams of carbon, 8.7 grams of hydrogen, 17.3 grams of nitrogen. Convert those to moles. Now, when we do that, we're going to get the empirical formula. And then we are going to say, to find the molecular, we're going to do molecular weight over empirical weight and see how many times that is. So that's one way to do it. The second way to do it is, since we're given what the molar mass is, we can say, let's look at 1 mole of our compound. So if we had 1 more mole of our compound, which is 162 grams, then we can figure out what's 74% of that 162 grams. That's going to be the grams of the carbon in that compound. And that way we don't have to do that second step. So I'm going to do it that second way, but either way works just fine. So I'm going to say I have 162 total grams, and it is 0.740, 74% carbon. So that gives me 119.8 grams of carbon. We'll do the same thing for the hydrogen. It's 8.7%, so that's 0.087. So this gives me 14.1 grams of hydrogen. And the same thing for the nitrogen. It is 17.3%, so 0.173. And this gives me 28.03 grams of nitrogen. Now I can convert each of those to moles. 1 mole is 12 grams. 1 mole is 1 gram. 1 mole of nitrogen is 14 grams. Let's see, so it's about 120 divided, so about 10 or so. I get 9.99 moles, which is about 10. This one gives me about 14.1 moles of hydrogen. This one gives me 2.0 moles. Now, if you did it this way, you don't then look at these numbers and say, oh, what's the ratio between them? You actually use those numbers. These numbers, if you did it correctly, should be very close to whole numbers. So this is pretty close to 10. This is pretty close to 14, and obviously this is 2. These are the numbers that you use for your molecular formula. Don't divide by the lowest number. Don't do anything. Just use whatever those are. Those should be, again, close to whole numbers. That is your molecular formula, not empirical, but molecular. So my molecular formula would be C10, H14, N2, and that is my answer. I think this method is a little bit shorter than the original method where you look at a 100-gram sample, find the empirical, and then do the molecular weight over the empirical weight. But either one works just as well. Okay, let's look at the next one. I think this one is a little challenging to think about. So let's read it together. It says, a metal M forms a compound MCl4. If the compound is found to be composed of 74.75% chlorine, find the molar mass of M and identify the element. So this one's a little bit different. So what are we trying to find? Well, we're trying to find the molar mass of M, and based on the molar mass, we want the identity of M. So let's think about molar mass. Well, how do you measure or report molar mass? Well, molar mass is in grams per mole, right? It's mass per mole. So molar mass is mass or grams over the number of moles. So let's see if we have either one of those. Well, Looks like we don't. So how can we find the mass and the moles of M? So let's, since we're given percentages, let's look at a 100-gram sample. So I'm going to say in a 100-gram sample, what mass of M do I have? I would have 25.25 grams of M. How did I get this number? Well, if I have 100 grams in my sample, 74.75 grams are chlorine, and then 25.25, the rest of the 100, is M. So look at that. I got the mass of M. 25.25 grams. Good. I'm halfway done, right? That would be the mass of M in a 100-gram sample. The rest is chlorine. So then what I could do is, in my 100-gram sample of the compound, maybe I can figure out how many moles of M are in there. And how would we do that? From the moles of chlorine. So let's take a look at this. This is how many grams of chlorine I have in my 100-gram sample. Let's convert that to moles. So 1 mole of chlorine is 35.5 grams of chlorine. All right, good. We got 2 moles of chlorine. Now, I can go from moles of chlorine to moles of M. How do I do that? It tells us it's MCl4, right? So in MCl4, there's 1 mole of M for every 4 moles of chlorine. Look, I got moles of M. 0.527 moles of M. So in my 100-gram sample, 25.25 grams are M, and I have 0.527 moles of M. So if I take my mass of M in my 100-gram sample divided by the moles of M in that 100-gram sample, if I divide the grams by the moles, I get the molar mass. My molar mass turns out to be 47.89. And this is grams per mole. So that's my answer for the molar mass. And then to find the identity, all you do is you look at your periodic table, see which element has a molar mass that's closest to 47.89, and that is titanium. And so that's my answer. Isn't that cool? Okay, let's look at the next one. Alum is a hydrated compound, KAlSO42H2O. Ooh, that's a mouthful here. I think they use alum in cooking. I've never really used it, but I've seen it like at Kroger and stuff when I go shopping. What does hydrated compound mean? Remember, hydrate means you have an ionic compound, but it has some water in it trapped in the crystal. And so when we write it, we write the formula of the ionic compound and then dot and then however many H2Os there. So this is a hydrated compound. It's a hydrate. It has water in it and it's crystal. It says if one heats 4.74 grams of that hydrate, 2.16 grams of water of hydration is driven off to form the anhydrous species. What is the formula of the hydrate? So let's think about what they're telling us and what we're asked for. So we are looking at this hydrate. Go ahead and change colors here. Which is KAlSO42, and we know it has H2O. What we're looking for is the formula of a hydrate, which means we just want to know what X is. Well, what is X? X is the number of moles of water, right, for every 1 mole of anhydrous. So let's see if we can figure this out. So I'm going to write it out here. X is the number of moles of water divided by the number of moles of the KAlSO4 Okay, so we just need to find those moles, right? Well, it tells us that 2.16 grams of water of hydration is driven off. Oh, we know the mass of the water, right? So let's go ahead and change that to moles. So 2.16 grams of water. Molar mass of water is 18 grams. That gives us 0.12 moles of water. Great. How about the mass of the anhydrous? Well, they tell us that the whole compound, the hydrate compound, is 4.74 grams. That's this whole thing, right, with the water. And they tell us when we heated it, 2.16 grams of water came off. So if we subtract 4.74 grams minus 2.16 grams of water, that's going to give us the mass of the anhydrous, which is 2.58. Right, because together 2.58 grams of the anhydrous plus 2.16 grams of the water, that makes up the total of the hydrate. So we're going to convert that to moles. 1 mole of my anhydrous is 258.2 grams. And this gives me 0.009991 moles of my anhydrous. So now, all we have to do is take the moles of the water, which we found to be 0.12, divided by my moles of anhydrous, which we found to be 0.00, basically 0.01. And so this tells us that that number is 12. So what does this mean? This means 12 moles of water for every mole of anhydrous. So my formula is KAlSO4 for every one of these, I have 12 moles of water. And that is my formula. Just so you know, the moles of water is usually a whole number. I have seen sometimes, though, that it is halves. So you could have halves there, but it's not very common. Usually they are whole numbers. So if you get like 12.1 or 11.9 or something like that, you can round up or down to get a whole number if you're pretty close. All right, very last problem. You see, we left lots of space for that last problem. So let's read it together. A compound is composed of carbon, hydrogen, and oxygen. The combustion of 10.68 milligrams of the compound in air produces 16.01 milligrams of carbon dioxide, 4.37 milligrams of water. The molecular mass of the compound is 176.1 grams per mole. Find the empirical and molecular formula of the compound. It's really long, right? So let's kind of slow down and think about what's happening here. So they're telling us I have this compound that's made of carbon, hydrogen, and oxygen, right? So carbon, hydrogen, oxygen, and call that X, Y, and Z. I'm going to, it says, burn it, combust it in air. So when you combust something, you're adding oxygen, right? And it tells us we're going to form CO2 and H2O, just like a regular combustion reaction, right? They give us a bunch of masses here. They're all in milligrams. That's kind of really bothering me. So I'm going to go ahead and change that to grams to put it in here. So 10.68 milligrams of the compound. So that would really be 0.01068 grams. They tell us that we have 16.01 milligrams of carbon. So in grams, that would be 0.01601 grams. And they tell us 4.37 milligrams of water, which is 0.00437 grams. Great. They also tell us the molar mass of the compound. And then they want to find the empirical and the molecular formula. So let's think about this. We want the empirical and the molecular formula. So that means we want X, Y, and Z. Remember, those are the ratio of atoms or the ratio of moles. Easier to find moles. So all we need is to find the moles of carbon, moles of hydrogen, moles of oxygen, right? So let's try to figure out how we're going to do that. So I'm going to start with moles of carbon. How would I find the moles of carbon in here? Well, I'm given grams of the carbon dioxide that's produced. I can use this to find moles of CO2 and then moles of carbon. So let's try to do that. So I'm going to go ahead and change colors. 0.01601 grams of CO2. First, I'm going to convert that to moles of CO2. So 1 mole of CO2 is 44.0 grams. And I don't want moles of CO2, I just want moles of carbon. And so I can say, well, for every 1 mole of CO2, how many moles of carbon are in 1 mole of CO2? 1 mole of carbon. And so that gives me 0.00036 27 moles of carbon. Great. Let's do hydrogen next. So for hydrogen, I can use the water. So 0.00437 grams of water. We're going to convert that to moles of water first. 1 mole of water is 18.0 grams. And then I don't want moles of water, I want moles of hydrogen, right? I'm trying to find moles of carbon, moles of hydrogen, moles of oxygen. So I can say for every 1 mole of water, how many moles of hydrogen do I have? I've got 2 moles of hydrogen. So when I calculate this, I get 0.004856 grams of hydrogen. I'm sorry, moles of hydrogen, not grams. All right, great. Next, I need to find oxygen. Now, that one's a little trickier. So, I'm not given the oxygen. I'm trying to find how many moles of oxygen are in my compound, right? I'm not given what this number is, right? I am given the products, but the problem is, if I try to find how much oxygen is in this and how much oxygen is in this and add them together, that's not going to give me just the oxygen that's here. It's going to give me the oxygen that's here plus the oxygen that's here, right? I'm adding excess oxygen there. So this is not really going to help me. But what I can do, because I only want the oxygen in my compound, only here. What I can do is I can figure out, because I figured out how many moles of carbon and hydrogen, right? I can change that to grams. So I can figure out how many grams of carbon and how many grams of hydrogen are in my compound. And since I have the total, I can subtract the carbon and the hydrogen from the total and get the oxygen. So I'm going to go ahead and do that in a different color. So I'm going to go ahead and go to grams. So for every 1 mole of carbon, there are 12 grams. And this gives me 0.004366 grams of carbon. Same thing for the hydrogen. 1 mole of hydrogen is there we go. Couldn't erase for a second. 1 gram. So this gives me pretty much the same number, 0.004856 grams of hydrogen. So now to find the grams of oxygen, I'm going to take my total for my whole compound, so this right here, so 0.01068 grams total, minus, and I'm going to take away from that my carbon and my hydrogen so that I get the oxygen. So 0.004366 grams of carbon and 0.004856 grams of hydrogen. This gives me 0.005828 grams of oxygen. That was kind of a lot of work, but now that we have grams of oxygen, we can go to moles of oxygen. So I'll do that in red so that all of our moles are in red. 0.005828 grams of oxygen. Change that to moles. 1 mole of oxygen, 16.0 grams. So this gives me 0.003643 moles of oxygen. All right, so let's see. We've got moles of carbon right here, moles of hydrogen right here, moles of oxygen right here. Now again, if you're pretty good with math, you can just look at these and figure out what the ratio is. If you're not, then you divide by the lowest number. So I'm going to go ahead and do that in a different color. Let's do it in black. Yep. Okay. So out of these, the smallest number is the 0.0003627. I'm going to divide this by 0.0003627 and do the same thing for all of them. Okay, this obviously gives us 1. This gives us 1.33 something. And this gives us 1. Now, that should give us the empirical formula. 1 to 1.33 to 1. Remember the empirical formula, it has to be whole numbers, right? So the 1.33, that's not really like close to 1, it's not really close to 2, so we have to do something. What we can do is multiply all these numbers by something to make it into an integer. So that's like 1 1/3, right? So if I multiply this by 3, and if I do that, I have to multiply all of them by 3. This gives me 3, this gives me 4, and this gives me 3. So my empirical formula is C3H4 and then O3. All that, and I'm done with the first part. Remember, it asked me for the empirical and the molecular. It's actually pretty easy after that. It's just a simple one more step to find the molecular, but this is my empirical, the simplest whole number ratio. So to find the molecular, what you do is you take the molecular weight over the empirical weight. So molecular weight is always going to be given to us. It is 176.1 grams per mole. My empirical is the molar mass of my empirical formula. So 3 carbons, so 3 times 12 is 36, plus 4, so 40, and then plus 3 times 16. So altogether, that's 88 grams per mole. And again, I'm going to write it on the side here, empirical weight. It's going to be 3 times 12 grams per mole, plus 4 times 1 gram per mole, plus 3 times 16 grams per mole. Just so you have it in your notes where we got that number from. So if you divide those by each other, you get 2. What that 2 tells you is that the molecular is 2 times the empirical. So if my empirical is C3H4O3, that means the molecular formula is C6H8O6. This is a really long problem. Requires lots of thinking, but you will feel so accomplished after you do it. I really like this problem. All right, that is it for the notes for today. You guys have a wonderful day. Bye.